Okay, welcome to this webinar on electrical thermography. It's not a long webinar, probably only about 30 minutes. We're just going to talk about a few things electrically related and thermography related, and we'll see where we really go from there. So to introduce myself, my name's John Willis. I'm ITC Level 3 certified. I've got over 19 years experience in the industry. I teach Category 1, 2 and 3 thermography courses. I do presentations at conferences, produce training content for ITC, and I look after the UK and Ireland, South Africa and Russia as a territory. And if we have a look at the ITC UK Training Centre, the Infrared Training Centre is the world's largest infrared training organisation with more expert instructors than any others and hundreds of thermography courses throughout the year to fit most applications, most locations and people's different schedules. The courses we offer are interesting, they're practical, a fast way to increase your credibility, enhance your career and build your thermal imaging business. We also offer IR training, certification and recertification in all aspects of thermography, including Category 1, 2, 3 classes, as well as specialised instruction in building diagnostics, roofing and other infrared applications. So what we're going to cover today, we're going to have a look at thermal image interpretations and what type of patterns to look for. We're going to have a look at things to remember. What is high electrical resistance? What is fault classification criteria? How do we perform an indirect temperature measurement if it's possible? And then some applications at the end. And I'm going to start off by first discussing some of the value that you can get from thermal imaging and how it's used in electrical applications. And we'll wrap up the entire presentation on why IR training is important. While infrared cameras are actually quite easy to use these days, it's understanding the physics behind what you're seeing. This is the essential part to being successful with this technology. So there are some key components that we need to understand before we look at electrical applications. These are emissivity, which relates to how well the surface emits radiation. Reflected apparent temperature, which relates to the background radiation that is reflected off the target and into the camera. The field of view, which is the camera's ability to measure a target at a distance. Conductive heat transfer and conduction patterns. Viewing angle and its effect on measurement. And finally, focus. We're not going to cover these key components, so they've been covered on previous tutorials. If you're at all unsure of what they mean, then have a look at on-demand tutorials on the ITC website where we find links to Introduction to Thermography and Capturing Great Thermal Images. Alternatively, if you haven't done, sign up to one of our certification courses. So the value of IR or the value of infrared, well, if we look at this daylight picture of the electrical installation, we can visually check for signs of discoloration on the components and cables. This could indicate that there's been an elevated temperature at some point. Just from the daylight picture, we're unable to tell if the target is hot or cold, whether it's good or bad. So, when we combine an infrared image with a daylight picture, we can see so much more. In the thermal image, if white is hot and black is cold, the phases themselves look balanced, so there's no real temperature difference between them. If we take a closer look at the brown cable, we can see that there's a thermal anomaly. At this stage, the camera doesn't tell us what the problem is, only that there is a hot spot or area. And it's the experience of the camera operator which will shed light on the problem. If you're a consultant, detecting the problem is probably as far as you want to go. You found a problem, so you leave it with the customer to diagnose and repair. When scanning electrical cabinets, the components with an infrared camera don't confuse the thermal anomaly with something that is designed to be hot. This example is resistors, especially those fitted to power correction capacitors, they can cause misleading hotspots and they aren't really a problem. I've seen quite a few reports where we've used classification criteria on components like this, and it really is a false anomaly. So here are some of the many considerations when looking at the thermal image of an electrical installation. We need to get the correct loading readings, the current readings, as heating with a low load is really serious. The equipment designation speaks of the importance in the process. Is this component more important than another for production purposes or similar? So we almost have to prioritize which components are important or not. Circuit consideration takes into account the position of this component in the circuit. So the circuit may be very important but have non-essential elements within that would compromise the circuit integrity. The time of use, which determines the amount of heating we see, but relating it to the cycle of use. 50% duty cycle would image much differently than, let's say, 100% or continuous. And understanding the environment and cooling effects. The application of these and the overall effect on how we image this component will affect our evaluation in many ways. Indirect measurements. This is where the source of the heat is situated behind another surface. We know the camera is not an X-ray machine, and the camera only measures the surface it can see. The image relates to the effect on that component from its internal source of energy, and we interpret the patterns. So anomalies found from indirect imaging can be misstated as the understanding of the severity or the extent that the internal problem is overlooked. And this is where the skill of the thermographer with the knowledge of the application is paramount. Understanding implications and the application of severity criteria is not to be underestimated. So what we encourage is thermographers to have the experience to judge an item from many aspects, not just, the measurement of temperature. And we will be having a look at two examples of severity criteria a little bit later. The first thing we need to do is understand what type of thermal patterns we're looking at. The thermal patterns show areas within electrical installations that might be defective. We can detect things like high resistance joints, imbalanced phases, faulty crimps, and even poor workmanship and design. Primarily, we are looking at patterns of conduction, and one example is a thermal gradient, which shows a changing temperature over distance. So recognizing thermal gradients is key to electrical thermography. If we have a look at this image here, we can see a connection, and the cables on the right-hand side of the connection entering and leaving the connection, they're very warm towards the connection, but they do get cooler the further away from the connection we are. And bad connections make up the majority of electrical faults detected. There is always a thermal gradient. With the hottest area at the high resistance, it should be pointed out that the resistance itself can be quite low, but will be higher than other good parts of the circuit. So by high resistance, we are speaking comparatively. The temperature of the connection will be related to the electrical load on the circuit, and if the current suddenly increases, then so will the temperature. So surveys should be undertaken under normal operation conditions if possible. These are examples of high electrical resistors on transformer connections. Both images are using the iron color palette where white is hot and black is cold. If you look closely, we can sort of see that there's some very definite elevated temperatures within both of the thermal images. This is an example on a multi-strand cable where some of the strands have broken inside the cable insulation. And we can see a hotspot occur when the load goes through the reduced number of strands at the point where the internal strands are broken. They appear in high voltage as well as low voltage. And in this example, the voltage is 90 kV, the load is 400 amps, and there's a maximum load of 440 amps on this circuit. There are a number of reasons for this. I think it's a great pattern. It looks wonderful, but it can be the case that one end of the cable, some of the strands have been cut back to make the connection. There can be a connection failure at one end of the cable, and some strands have been broken or melted away. The cable can begin to unravel, creating a contact resistance between the strands, or after a high resistance fault has been detected, it can be the case that the bad connection has been cleaned. If the person carrying out the repair does not clean between individual strands, there will be contact resistance between the strands, and usually one or more of the outer strands will carry all the current. It is important to recognize that the problem can be at either end, or in fact you have separate problems at both ends that contribute to the overall anomaly in the thermal image. When the load is not unbalanced, when the load is not balanced, the average global temperature differs from one phase to the other. If we have a look at the thermal picture here, we can clearly see that the right-hand phase is warmer compared to the others, and there's no real localized hotspot. In electricity, we exploit the phenomenon of induction, particularly in the case of transformers, where we use mutual induction to transform electricity from one voltage to another. However, as we do have so much AC electricity, it's not unusual to find unwanted inducted heat on some other metalwork located near the electricity or electrical components. Induction will take place on metalwork, and in some cases it can be difficult to establish the exact reason why this happens. But we can say that it does happen as a result of the location of the metal and its proximity to the electricity. We find that sometimes poor design of electrical panels can create some quite phenomenal induction patterns. And in this case, we've got an open circuit. The top fuse is blown. The fuses control a capacitor bank, and the fuse blew because of a problem with the capacitor. It's very easy when you're using a thermal camera to always look for hot problems in the thermal image. But, with thermography, we can easily determine that one fuse is colder than the other. This is often the result of the fact that one of the fuses is not carrying any load at all. And it can be the case that the fuse with no load is blown, and in some cases it can be on an item that may not be noticed readily by maintenance personnel. Just a note here, don't overlook a cold component on a circuit because it could be the major problem. And this is a rare image. The energized ground or earth cables are often overlooked as there is seldom a thermal gradient. You can easily determine that the temperature is the same right along the cable, and therefore that the heating is due to load. What people often forget is that the purpose of earth cables is to provide a path for the current to flow in the event of a fault. And most faults are instantaneous, so the current along the earth cable is only there for a very short time. And although this can cause heating, it too is only for a very short time. So other faults, however, will cause current to flow along an earth cable on a continuous basis. This one here is more dangerous. If an earth cable is carrying a current on a continuous basis, it could be due to a number of reasons, but it basically comes down to a fault to earth, on a permanent or at least a semi-permanent basis. And as the earthing system is not normally designed to take continuous load, the components are likely to fail if exposed to excessive load. And once a component fails, the fault path is now gone, and typically you are left with some live equipment looking for a new path. And this can be live metalwork, either on electrical equipment itself or in extreme cases, other metal like pipework or building structure. And this can stay like this for quite some time, waiting for a new path. Eventually, however, it will find a path through a person, animal, or object that happens to come in contact with the live metal. And as thermographers, if we do come across high temperatures on an earth cable, it should ring alarm bells straight away. We then should check if the current is a current, and if so, how much. So a clamp meter is the best way to do this. And if there is a current flow on a cable, we need to highlight this immediately to the relevant people. The very least we should do is contact an engineer familiar with the site electrical system and discuss it with them. The engineer should understand the specific system of earthing used at the site, as there are different systems. When it comes to motor problems, the lubrication problems can be things like under-lubricated, over-lubricated, contaminated, or incorrect lubricant. Incorrect fitting can be misalignment, imbalance, or structural looseness. And there are many types of bearing failures. So while we may detect the problems with thermography, we're unlikely to understand the exact reason why we're seeing an elevated temperature. So we may need another form of technology like vibration analysis to give us the answers that we can't find. Short circuits in windings. Motors are classified. The insulation is classified as, A, B, F, etc., according to the ability of a motor to resist aging and failure due to heat. And when operated normally at a maximum authorized temperature, the average life of a motor is around about 20,000 hours. An operating temperature below the limit will result in longer life. On the opposite, an operating temperature above the limit will considerably reduce the life. So as a rule of thumb, it is admitted that for each 10 degrees C below the rated temperature, the life will double. And for each 10 degrees above, the life will be halved. Of course, other factors affect temperature life of the motor. So looking at infrared measurement techniques, we have identified why we can see electrical problems with infrared. What we're going to look at now is something called indirect temperature measurement. Fault classification criteria, really, which is we found a problem, how do we classify how serious it is? And then with electrical thermography, at some point we're going to come across infrared windows and meshes. So we're just going to have a look at a few of those and, you know, what they can do for us. So with indirect measurements, you need to remember the internal temperature will be a lot higher than the external temperature. So we need to adjust our severity if we cannot overcome the indirect nature of our survey. And if we have a look at this two installations here, these are indirect measurements of buzz bars. So if you have a look at the two thermal images on the right-hand side of the slide, you know, they're a long way away, but the camera is doing a good job in picking up an elevated temperature, and we can also measure a delta T. The heating source may be some distance away, which it is, and for this reason, it's difficult to estimate the internal temperature accurately. Added to this problem is the fact that a lot of these have low emissivity finish on the exterior, which means they could be reflective. Some knowledge of the construction and assembly can be of benefit. It can give us an indication of where the joints are. So local heating near a joint could be viewed as a possible indication of a problem with the joint, and the temperature inside may be really high, even though the external temperature rise may be low. So luckily, we have daylight pictures that show how these bars are connected at the unions. And I think it really does help to understand that if we get a high resistance on those connections, we see it quite clearly. What about if you're confronted with a room full of panels or an electrical panel like this? You know, if we were to view this panel, as we have done, if we look at the daylight picture and the thermal picture, you know, we can't draw much information from this. You know, maybe that the panel door uniformly is a little bit warmer than the surroundings. If we now open a panel, you know, the problem can only be seen after the panel has been opened. So with infrared, the doors of electrical panels are what we class as opaque solids, and it's not possible to truly assess electrical systems without opening them first. We may open them and find perspex or lexan. If they're behind the panel doors, they also need to be removed. And there are people that believe that just because you can see through them in visible part of the spectrum, then you must be able to see through them in the infrared part also. This is untrue. Perspex and lexan are thermally opaque, just like the panel door to the infrared camera. And you may be performing an inspection where the previous thermographer carried out a survey without opening any covers. And it's difficult to convince the end user to open the covers if they've experienced this. An alternative to opening covers is using infrared windows, but you should check with the switchgear manufacturers before retrofitting them to ensure that the windows are correct for the installation and do not invalidate the equipment certificates. We're going to have a look at some examples of infrared windows a little bit later in this presentation. Fault classification criteria. Within thermography, we've got a really useful standard. It's ISO 18434-1. The name of it is Condition Monitoring and Diagnostics of Machines for Thermography. Now, in Chapter 13, there is a whole section on severity assessment criteria, and it can be established on individual machines or components, and this method is based on many factors, including safety of personnel, temperature rise versus historical data that establish the rate of deterioration, and also time to failure. Applications should include temperature rises of critical machines, mechanical components, bearing temperature rises, electrical supply, or connection rises. Could include fluid leaks and losses, or even a number of tubes clogged in a fluid heat transfer type equipment. So within chapter 13, if you can get your hands on this standard, have a look at it, because it will really help to establish severity assessment criteria. To be able to measure full classification criteria, we need to be able to perform two tasks. The first one is we need to be able to perform quantitative measurements. This means that we need to be able to set the camera up, we need to set the emissivity, the environment, and know the surface and take an accurate temperature measurement. The second point is we need to be able to do this twice. So it could be at 2 points on one component, or it could be between one thermal image and another thermal image. And that measurement is called a delta T. And all fault classification criteria is based on a delta T measurement. So this is an example. It's from the National Electric Testing Association. This is an American classification criteria. There's quite a few things missing from this. Things like indirect considerations, the size of the target, the environmental conditions, loading, circuit importance. But if you have a look at this, we're looking at anywhere between 1 and 3 degrees on a similar component, is possible deficiency, warrants investigation. 4 to 15 degrees indicates probable deficiency, repair as time permits. Anything above 15 degrees, we've got a major discrepancy, repair immediately. So these classification criteria, they're not set in stone. If we have a look at another example, and this is the example that we use within ITC, we've got a traffic light system. And the definitions of the class A, B, and C, they don't change. But what does change is where the blue text is. We've got flexibility there to adapt this classification to whatever we're looking at. So a class A is a really serious anomaly that requires immediate attention. So we've got a temperature difference, a maximum temperature over 80 degrees or a delta T over 30 degrees C. We've got a class B, which is a serious anomaly that requires attention as soon as possible. So we've got a delta T between 5 and 30 degrees C. We've got a class C, an anomaly that requires monitoring and a checkup at the earliest convenient time. We've got a delta T up to 5 degrees C. So if you can imagine using this in a reporting structure, we can have all the different classifications of that component appear on a summary page towards the front of the report. And this in turn sets the repair priority for the findings of the survey. So an example of using fault classification on a 3-phase supply, if we have a look at this, the delta T is 38.4 degrees C, which means it's a class A problem straight away. And you can see the importance here of having good understanding of thermography and being able to measure a delta T correctly. If you don't, if you miscalculate the delta T, you could misclassify how serious this problem actually is. This example shows we've got a delta T of 23 degrees C, and based on our classification criteria, this is a class B problem. So you can sort of see it works on HV as well as LV. This image shows a delta T of 17.7 degrees, again, which is a class B problem. And this is the last image. It's a class A problem with a delta T of 34.1 degrees. So from these examples, we've seen how simple it is to classify the fault found, which in turn helps in reporting the problem and working out repair strategy. This one here, if we've got PVC cable and the sleeving is burned off the cable, what we can see is that the gas has ignited and damaged the insulation in the middle of the cable. So the delta T in this image is 91.3, which pushes this into a class A situation straight away. So talking about windows, a faulty connection, which is what we're looking for, can be an explosion waiting to happen. And the more we disturb its environment, the greater the chance we can cause it to trigger. And we've probably all seen photos of arc flash events or videos of arc flash events, show even steel covers will not always protect someone nearby from an injury. but they are better than no cover at all. Now, with an infrared window, it won't totally protect you either, but it's better than the entire cover or panel being removed or open. Though done for safety, infrared windows can make the thermographer's job a lot easier. We just open the window cover, shoot, and we close the cover. No bolts to remove, no safety interlocks to defeat, no latching hardware to disturb, etc. And the technician may be able to wear a reduced level of PPE gear, making the thermographer more comfortable and be able to run the equipment much better. So to answer the question, if you haven't seen one before, what does a thermal window look like? This is what they look like. And they can be made of many, many different materials. So the infrared windows, also called viewports or IR crystals, can be 7 different types of IR transmitting material. The lowest cost are infrared transmitting plastics and fluoride crystal. Salt windows such as barium fluoride have a higher cost, but more durable is something like a zinc selenide window. And some infrared windows are a steel mesh that is around about 50% holes and 50% metal, and the holes are too small to poke steel tapes or fingers through. Commercially supplied infrared windows will have a cover that should be in place when not being used, and also the cover provides protection for the window to keep it clean and dry and out of harm's way. Now, an excellent additional benefit for using infrared windows is you will do your surveys not only safer but faster, and you won't be bothered with defeating the interlocks, as we've said on previous pages. Be certain that the device is UL rated and listed for the purpose, and just remember that you need to compensate your reading, as an IR window isn't 100% transmissive. And if you're unsure on this, it may mean that you do need to attend a training course. There are other tools in the toolbox that we can use. We must know many factors for the interpretation of images, as you've seen, and one of the most important is taking the current reading of the equipment we are imaging. Apply test measurements safely within the rules of your organisation or your procedures that you follow. When it comes to other tools, we must also acknowledge that infrared may not be able to show what is wrong, only that there is a problem, and we should be aware of other testing technologies to assist the testing process. So if we've got a whole room full of motors, we may use vibration. If we're looking for air leaks, or arcing, it could be ultrasonic. If we want to analyze the oil in transformers, we could perform oil analysis, or even motor current analysis. So thermography is excellent at finding a problem, but we may need other tools to help understand exactly what that problem is. So moving on to examples, we're just going to have a brief look at some electrical applications. And the first one we're going to have a look at is solar panels. Wherever you go now, you see whole fields of solar panels. And this type of panel is a polycrystalline silicon solar panel. And we may look at the image and sort of think, well, actually, oh yeah, we've seen a problem because we can see some hot areas on that panel. But in essence, the cells are warmer due to a shadow created by a tree in front of the panel. And you can recognize the shape of the glass surface of the IR picture. The cells will cool down when the shadow moves away. And this is just one consideration of looking at solar panels with thermography. These are defective cells. These are solar panels on a roof. We've got 2 defective cells in that panel. They're just not able to convert the energy from the sun into electricity, and they've really just got hot. And we've used quite a high resolution camera on this. It was a 640 by 480 pixel resolution. When we look at cooling and transformers, most of the cooling tunes in this image are not working. What I've done, I've put a profile or a line tool in the software to show the comparison between working and non-working cooling tubes here. Great visual. We don't necessarily need to measure. We just need a visual on this, a qualitative approach to say, yeah, these are working, these aren't. If we have a look at this one, the image on the left-hand side, the cooler section in the left-hand image shows a problem with cooling on the transformer. We've identified it with the camera that we've got an anomaly. On further investigation of this, the valve at the top of that compartment was blocked, so it was unable to do its job. These are oil-filled circuit breakers. What we're looking at is an indirect measurement that the heating source may be some distance away. And for this reason, it's difficult to estimate the internal temperature accurately just by looking at the outside. It must be remembered that these oil-filled circuit breakers, sorry, yeah. So the external rise may be really low and still indicate significant internal rise. So maybe 2 or 3 degrees delta T on the outside could indicate that we've got a 10 or so degrees delta T on the inside. Try to take advantage of geometry when we're looking at things. This is actually a contactor. We've got some copper connections coming out of the bottom of the contactor. Try to take advantage of geometry, of painted areas or of some high emissivity attached components. And if we just look at the copper buzz bars, we'll have difficulty taking an accurate temperature measurement or detecting a problem because they are shiny, they've got low emissivity. However, if we look closely at the paint on the bolts, there is a different emissivity on the paint compared to the bolts that could give us an indication of temperature. There is actually, between the top bolt and the bottom bolt, we've got a delta T of 10 degrees. So there is a problem on this contactor. When we've got a poor installation, conductors or cables of the wrong size, this is a 40 amp molded case circuit breaker used on a machine for a disconnect. The breaker is 3-phase, but only 2 of the phases are actually used. And if we notice the heat on the load wires in comparison to the line conductors, certainly a sign to look a bit deeper. Even in the infrared image, the load conductors appear smaller than the line, and the line is diameter 6 and the load is diameter 12. So this is an example of the concept of infrared by looking around. You know, don't be afraid to pan around and just see if you can pick up on things. The machine wiring was not part of the original survey, but as covers were removed for access in the area, it was noted on the report. Conductors, crimps, the transition points of the conductor to the plate or the bolted pad is a common point for imaging problems. Here we have a hydraulic crimp on a parallel feed to this equipment. Now, parallel feeds have got their, there's a bit of theory needed to understand exactly how parallel feeds work. One of the lugs is warmer than the other in this image, and the warm lug has the area box around it. The real problem is that the hot one is the good one in this case. The current on this termination is mostly thrown through the good connection and overheating it because the other cable, the lug, is poor and is not conducting as it should. So the visual clues of damaged insulation give good indication of previous or continuous overheating. And quite a rare one, capacitors and batteries. These are generally passive devices with not much heating at all. This case certainly shows one heated much more than the other, which only shows a slight warming over the middle capacitor. Examine this circuit and determine if the discharge resistors are engaged for some reason or if the capacitor is damaged. Secondary testing with other methods is warranted in this case. And low oil in a substation, the fill level of these is crucial for the cooling. The oil expands and flows into the radiator tubes to release the warmth into the environment. We can quite clearly see in this image that we've got quite a few different levels of cooling happening. So something here, like an oil level, is causing this issue. And we've seen a similar image to this, you know, transformer section of valve closed. This one is the easiest to interpret. The section valve was not opened after transformer service. So we can see that black line going down towards the left-hand side of the image. Moving on to some HV things. This is a flexible strap connection transition from the round buzz bar to the breaker. You know, the image is quite clear. The strap is warm compared to the other phase. This by itself indicates that there is an issue somewhere on the piece. Probably a loose connection on the bolted parts. This image is out of focus, but it's a drop lead. It's a mechanical tap connection, and all the same consideration from the last image where this is bare metal, and again being outside for a long while, so it is oxidized, so it's got fairly high emissivity. This is a high voltage air switch. Where the area box is, the little green square, we can see one finger of the switch receiver looking quite warm. And with the current levels very high on these units, the potential to have a major issue is ever present. Just remember that in a parallel connection, which is what these fingers represent, the hot one is the good one. We've got oil filled switches. We've seen these similar ones to these. The implication with these is that the heat inside these units and what's displayed on the exterior is quite different. There is some guidance that a 3 to 5 degrees C is enough difference measured on the outside to take this out of service. My caution is that the indirect differences on these large substation components should be taken quite seriously. And just going back here to something of contactor, if we have a look at this contactor, we can see that the right-hand phase is much warmer than the others. You know, we've got to ask ourselves, what is the problem here? Could it be a load imbalance? Could it be a loose connection? Or the third option, could it be an internal contactor fault? What I'm going to do is give you the answer to this in a moment. We've only got a couple of slides to go. So, could it be an imbalance, a loose connection, or an internal contactor fault? So really to conclude, we need to be able to recognize IR conductive heat patterns to be able to identify electrical problems. You know, where possible, open panels, as this will give you the best results. Infrared windows and meshes can be used in situations where panels cannot be opened, but do remember, if you're looking through windows, you're going to have to compensate because infrared windows are not 100% transmissive. Fault classification criteria is a recommended way to categorize faults found. You don't have to use what we've shown today. If you're competent enough, you can make your own classification criteria. And also understand what applications the infrared camera can be used to survey. Don't be afraid to have a look around during your survey. So if you want to learn more, head to www.irtraining.eu. That's our website where you see a complete list of training courses, registration information, details on the class, location, and more. Finally, we also have a number of additional IR training modules in our online learning management system that includes the basics of camera operation, overview of applications, and theory that I encourage you to try. Some of which are free, but are all great and engaging and are another educational resource that you should take advantage of. Speaking of infrared education, if you've not completed a certification course with ITC and you want to learn more, give me a call. Now, going back to this image, we looked at this just now, and you might have an idea as to what the problem is. The actual problem with this contactor was the internal components were pitted and had gone high resistance. So on the right-hand phase, we've got an elevated temperature on the bottom cable, and the resistance, the heat from the contactor was conducting out through that cable. Just like to ask or to thank you for listening to this webinar. If you've got any questions, get in touch with ITC. You've got my email address. Send an email to me. Thanks very much for listening.